And if all four of our speakers could come back up, he'll be back in just a moment, so.
I can possibly help answer the last question in a way, is that at Mercury, of course, we observed the exosphere with masks, and the different elements had different associated temperatures. For instance, the magnesium was associated with a 4,500 Kelvin temperature associated with the scale height. The sodium at Mercury is more or less 1,200 Kelvin with high, probably a high temperature component as well. And calcium, the calcium that we see is extremely hot. So there's got to be a mix of processes involved in these exospheres.
Can I follow up on that comment?
Yes.
So I totally agree, and impact vaporization may be the dominant, but on Mercury, you can have the proton precipitation coming down, and people will call it sputtering, but when you have this event, which is driven by an ionization event within the material itself, then you can have neutral sodium and potassium and the constituents of the mineral coming off of these with extremely high velocities.
Yeah, that's true, and I think the sputtered component is more difficult to observe because it's very hot. The surface number densities are going to be low, and the exosphere is actually going to be a corona because most of it is escaping. So that's where this extended high temperature component comes in, and we really, we can see that by observing the tail, the escaping part.
And that is done.
Well, there are people, yeah, Jody Wilson has done some of that, so he can.
Can I ask another question related to this? So we've been working with Menelaus on trying to do some of these measurements, not so much for the moon, but for Mercury. And with photon-stimulated desorption, you can get a very low velocity distribution. Can you see that? Can you see the slow ones?
At the moon?
Yeah, because the physics should be the same there, yeah.
Yeah, like Tom said, the data that our group took with the McMath, the very high resolution spectra, there's been a range of scale heights measured, and there is a cooler component.
But it's really true. If you're going from the lunar surface to one kilometer, you're looking at all the low velocity stuff.
Mm-hmm.
So you've measured it. If you don't see a lot of evidence for that scale height there, it's not there on the moon. You're looking right where it should be. Let me give that back to you before I talk.
Okay, so do we have any further discussion on the other presentations that were given during this session? There's 2, 3.
Hi, so I have a question for our first speaker today. I don't remember your name, I'm sorry. So I'm a high school student from Wisconsin, and we were kind of doing research on that lunar water and kind of the migration of it, and we had run across a lot of research that showed the migration of that water to the poles, which was shown in your simulations with that kind of band of concentration of water and hydration at the poles. I just have a question as to why directly on the poles there was not that water concentration, and this might just be a question of ignorance. I'm not 100% sure, but.
No, yeah, I tried to address that. It's just a matter of simulation time.
Okay.
The flux there is lower, so it just takes longer to simulate
Okay.
the buildup right there, right? So those simulations took about a week, and that was 3,000 some odd lunar days, right, in order to fill up that. So what I did is I just, fit it and plotted it, or plotted and fitted it to kind of extrapolate the time that would be necessary to fill in that gap. and you were looking at about 20,000 years, right?
Okay, so
simulating that would have been like years on the computer. And
Okay,
I just,
so it
I
would-
just stopped it after
It
that.
would fill in
Yeah.
eventually over time?
Yeah, yeah.
Oh, okay, that makes sense. Thank you.
Mhm.
Tom, I was just going to comment on your observation that we still don't understand the process. And, you know, the reason is experimentally, of course, sodium is a nightmare to work with. Mady did a lot of work on this, and Tom Orlando's group is as well. And, you know, from the Mady papers, they were never able to see photostimulated desorption from the materials until they deposited sodium on them. So they had to pre-dose materials. And it's interesting that there's no thermal component, because at the temperatures, certainly of Mercury and the moon, you should see thermal sodium desorbing through, you know, just you know, the temperature increase during the day. And, you know, that kind of indicates that it's a lot more reactive, I suspect, and that's why it's maybe not there.
Well, I don't argue with you, I just tell you what we see. You know, I can't do anything about it.
Sure.
Yeah, and I agree, sodium is miserable to have in a laboratory, but so are a lot of other things. Oxygen's miserable to have in a laboratory. I mean,
Just to
single
some
oxygen
degrees,
is, yeah, at
but
least in a neutral mass spec.
you know, one of the problems with sodium and a lot of these alkali metals and stuff is once you start studying them, you're always studying
Yeah.
them. You basically have now a dedicated chamber, which, you know, it's problematic.
Get this back.
Bill, you had raised your hand.
Yeah, I just, you want, and then you can, I'll.
Okay.
This question's for Tom. When Laddie orbited for a short amount of time, 6 months, we did look for correlations between sodium and potassium from EBS and then the meteoroid bombardment.
I know.
And we noticed that actually the sodium led the meteoroid vaporization, and so it preceded it, and so we found it wasn't very well correlated, even during a very large meteor stream. So I was wondering if you had any comment on why that might be.
No, I don't. As I say, we just took the simple idea that when we have, if we do these observations and then we look to see if there's evidence. I didn't mention we had one observation where during Geminid meteor shower, but on the Earth it's a meteor, but you know, and on the Moon, we can only do what we can do. I'm not that familiar with the Laddie results in terms of leading the impact process. So I plead partial ignorance.
Hi, this is for Brandt. So a quick question I have is, you know, it sounds like in your description, it almost sounds like there's a water fountain around the subsolar point where the recombinative desorption operates to make the OH.
Okay, yeah, sure.
You know, well, you know,
Yeah, yeah.
you can just picture and then the waters come out. Is there a latitude or a solar zenith angle where the OH diffusion slows down and so you can no longer get effective recombinative desorption? Then it's just hops from that edge. What latitude or solar zenith angle where would you think the process starts to degrade?
Right, so we did, after about 75 degrees, it shuts off and it just constantly adds and adds to that, right? But also I'd like to point out that, you know, this model is basically version 0. I didn't really include diffusion into it. My approximation for that was just that once it's implanted, if it's warm enough, it'll reach the surface in about 2 hours given literature diffusion constants. And so, yeah, this is something that definitely needs to be incorporated into later models.
Okay. Oh, okay. Good.
Any further questions or discussion? Then I think we can wrap up early and go to break. Thank you, everyone.